Okay, what we want to do with this next set of videos is discuss a really important application of the linear differential equations with constant coefficients that we've been discussing. And that's the harmonic oscillator. The harmonic oscillator is the name of a physical system. Anytime you have a physical system where how to define a harmonic oscillator. Think of it like a mass on the end of a spring. When you have a mass on the end of a spring and when you stretch out that spring, there is a force that wants to restore the object back to its what we call the equilibrium position. And if you take that same system and you compress the spring, right? Then there is a force that wants to restore the object back this way. So there's always this sort of restoring force, which is trying to bring the object back into some kind of equilibrium position. That's called a harmonic oscillator. And a mass on the end of a spring is a great example. But it also arises in the study of like circuits. It also arises in the study of things like pendulums. You can imagine, you can see that there is a restoring force happening with a pendulum, and they're well approximated, it turns out, by harmonic oscillators of the sort that we'll be studying. It also arises in the study of like when you have like a diatomic molecule, that is a molecule with two atoms, and that thing is vibrating. You can model that vibration there using a harmonic oscillator. So quite ubiquitous, quite useful in the study of vibrations and an oscillation. Very worth our while. So that's what we're going to spend some time doing. So let's talk about it. Always good to draw a picture. And the picture that we are going to very frequently appeal to is, again, the picture of a mass on the end of a spring. So imagine that we have like some kind of wall here. We have a spring, which I'll depict like this. And then we have an object of mass m attached to the spring. Now, if everything's at rest, the mass is not moving, the mass, and it's in equilibrium, then there's going to be some kind of equilibrium position, which will denote x equal to 0. And maybe the equilibrium position is right there. So right now, as depicted, this mass is stretched out. This spring is stretched, okay? And we'll call the position of that object, we're going to call that x. And we're going to take x to be positive in this direction. This is the direction of increasing x, like that. Okay, so when the spring is extended beyond the equilibrium position, we'll say that x is positive, and when the spring is compressed, we'll say that x is negative. Okay? Then what forces are we going to consider in this system here? Well, first thing I want to note, we're only going to be considering the motion of this object along this one-dimensional axis that I've got pictured here. Okay? Only in the horizontal direction is according to this picture. All right? So we're not thinking about any vertical forces or anything like that. Now, what forces are we going to allow ourselves to consider? One force that is incredibly important is called the spring force. The spring force is that restoring force that I was telling you about earlier. And again, it points when x is positive, it points in the negative direction. And when x is negative, it points in the positive direction. So we're going to denote that state of affairs by a negative k times x. And the fact that this spring force is proportional to the position is sometimes referred to as Hooke's law. Maybe you've heard of that. Okay? But that's one of the forces that we're going to be considering. And again, it points in this direction, like this. Opposite, in this case, always back toward the equilibrium position. Let me say it like that. And then we'll also consider a frictional force. Maybe I'll call it F sub drag. I don't know, friction. F sub fric. Okay? And just like we considered with free fall, remember when we did free fall with air resistance? We modeled the frictional force as being proportional to velocity. So we'll do the same thing here. It's going to be C times V. And again, because this opposes the direction, it's going to be, we're going to have a negative sign here. So this is going to be a force pointing in this direction also. Okay. Negative sign. And by the way, another way of writing this, because remember, V is the derivative of X in this case, that's negative C times X prime. Well, maybe I'll write it as dx dt for now. And later we'll just write it simply as X prime. Okay? All right. And then finally, we have the possibility of there being some kind of external force, which I'll just call X. F sub X. This is just going to be, I'll just denote this one F. Okay? And this is going to be some force pointing perhaps in the positive direction. Like you might imagine there being some kind of rocket booster or something like that on your object M, which is going to be some kind of external driving force. Okay? Now, how can we build a differential equation out of all of this data? Well, of course, the crucial law that we're going to use is Newton's second law, F equals ma. F net, the net force acting on this object, is what's going to be equal to mass times acceleration. So ma is going to be equal to the sum of all of the forces here. So that's going to be F spring plus F fric plus F x. This is the net force acting on the object. But we know A is x double prime. It's the second derivative of position. F spring is negative kx. F fric is negative cv, which is x prime. And this external force we'll just call F. Now I'm going to move the negative cx prime over, and I'm going to move the negative kx over, and I get the harmonic oscillator equation, mx double prime plus cx prime plus kx equals F. And this is called the harmonic oscillator. And how is this different from, the kind of second order linear differential equation that we might have seen in the past? Well, in this situation, we have some key assumptions. In this case, notice, please, that the coefficients, yes, they're all constants. So this is a constant coefficient equation. However, they're all positive constants here, or at least non-negative. So let me say that. M here is going to be strictly positive. C could be 0. We'll allow ourselves to consider the situation where there is no frictional force. So we'll say that C has to be greater than or equal to 0. And finally, we'll require that K be positive also. That there is a non-zero restoring force, what we're calling the spring force. Okay, so these are key kind of assumptions that we're going to bring to bear, and it'll be useful for us when thinking about the harmonic oscillator. Okay, and just a few more words, just a few more vocabulary words here. We're going to call this a forced oscillator if F is not 0. So if the external force here, this F right here, is not 0, then we're going to say that this is a forced harmonic oscillator. If this F, oh my God, if this F right here is not 0, then we're going to say that this is a forced oscillator. And it'll be unforced or free. I'll probably use free a lot. If big F is 0. Okay. It will be damped. A damped harmonic oscillator if C is not 0. And it will be undamped otherwise. And we'll allow ourselves to think about such things, okay? One other note. So here, make sure you understand, the dependent variable here is x, and the independent variable is time, t, okay? Furthermore, this F, external force here, need not be constant. If it's not constant, then it depends on t in some non-trivial way. That's what I mean by non-constant. In other words, we could have a force, an external driving force, which is really large for a little while, but then tapers off or something like that after some amount of time. In other words, something non-constant through time. Yeah. And that's going to have interesting dynamics, of course, on our harmonic oscillator, if we consider such things. Okay, that's the harmonic oscillator. In the next video, we will talk about the undamped free case of the harmonic oscillator. Okay, see you in the next one.